Hello, my name is Hanna and I am a student at Gdańsk University of Technology and I study mathematics. The topic of my bachelor's thesis was the use of evolutionary algorithms to solve mathematical problems using the R language. Today, I would like to focus on a specific problem, which is the traveling salesman problem. I would like to introduce you to the genetic algorithms. Then we are going to talk a little bit about what is the traveling salesman problem. At the end, I would like to share results I obtained thanks to GA package from programming language R in finding an optimal solution to the traveling salesman problem. Let's begin with a short introduction to evolutionary algorithms. Evolutionary algorithms are stochastic algorithms which are inspired by the evolutionary process that we know from biology. The main reason why these algorithms were created was the will to upgrade the way of solving the optimization problems. Methods which searched the space point by point were just too time-consuming, while others often fell into local extremes and had problems getting out of them. Almost at the same time, the four types of evolutionary computations were independently created across the globe. Their common feature is that they generate and analyze many solutions simultaneously, which are called population of solutions. In the state space, they are treated like individuals in a certain environment, which means that they will undergo operations similar to those of the living creatures, which are crossover and mutation. Same as it is in nature, individuals which are better adapted have a bigger chance of offspring and creating a new generation. The most popular and the best described method is the genetic algorithm. Distinctive thing about it is its binary representation of individuals, which means that each individual has its own genes. As it is the least abstract evolutionary algorithm, I think it's the easiest one to gain some intuition with, and it is the one implemented in GA package. Let's analyze its scheme of action. We start with the initial population of individuals, which are potential solutions to the task we consider. We choose individuals by randomly drawing them from the solution space. We calculate the value of fitness function for each of the individuals, which, for example, in the maximization task, is simply the examined function. Values of this function allow us to decide which individuals will be the best to use in the next stage of cycle. Then, the individuals undergo genetic operations, such as crossover and mutation. Lastly, we check the postcondition. If it is true, that means we found an estimated solution, otherwise, we repeat the whole process. So firstly, we draw the initial population. There are various methods of selection, one of which is the roulette method. That is, the size of the area of the roulette wheel corresponding to an individual is directly proportional to the value of its fitness function. Then, thanks to the fitness function, we can assess every individual to check how close to the desired solution the individual is. To create a new generation, we make a selection among individuals from the initial population. Those which will be chosen will be named the parental population. In the next phase of the cycle, we create a population of descendants by using the genetic operations, which are crossover and mutation. Crossover means choosing a random pair of individuals. Usually, the probability of this operation belongs to the interval 0.6 to 1, because we want to give as many individuals a chance of procreation as we can. Then, we draw a crossover point for each pair, which will determine chromosome cut point. For example, Let's assume that crossover is happening on two individuals, and we drew that cut point is, for example, 4. If that's the case, we cut off everything after this point and swap everything that is left after point 4. Thus, we get two new individuals that have different set of genes. Mutation, on the other hand, is the operation with probability we want to belong to the interval from 0 to 0.1, because mutations in nature do not happen very often. If the probability was greater, it would introduce too much randomness in the development of the population. It is often mentioned in the literature that mutation provides a supply of fresh blood. It is also there to prevent the irretrievable loss of genes that may be required to find the solution we want. For example, having a binary encoded individual, the mutation is done by changing 1 to 0 or 0 to 1 at a random place. At the end of the cycle, all of the individuals that belong to the generation are assessed again. We are checking right now whether the algorithm postcondition is met. If that's the case, we lead out the best individual, who is the solution to the considered task. If requirements are not met, we create a new generation, continuing the cycle again. There are different methods of determining postcondition for the task. It may be the number of generations, that is the number of iterations in the algorithm. It can be the time of the algorithm's operation, or obtaining an acceptable quality of the solution. Let's talk now a little bit about the traveling salesman problem. The traveling salesman problem is the problem of finding the shortest possible route that visits every city exactly once and returns to the city where the route started. Traveling salesman problem can be modeled as an undirected weighted graph, such that cities are the graph's vertices, paths are the graph's edges, and a path's distance is the edge's weight. Then we can formulate the problem in terms of graph theory. Given a complete weighted graph, find a Hamiltonian cycle with the least weight. How can we obtain the solution to this task? The traveling salesman problem is an NP-hard problem in combinatorial optimization, which means we are faced with non-deterministic polynomial time hardness. Moreover, the most direct solution would be to try all permutations and see which one is the shortest. So using brute force search. The running time for this approach lies within a polynomial factor of O of n factorial, which is the factorial of the number of cities, so this solution becomes impractical even for only 20 cities. Distances between every pair of cities can be represented as a matrix, which on the diagonal has zeros, because the distance from city 1 to city 1 is 0, of course, and the distance between city A and city B should be equal to the distance between city B and city A. We can put this matrix in our program. Next, we have to decide what our fitness function will look like. We can use this formula to calculate routes. That way, we can compare the individuals in the population. We have now every tool we need to solve the traveling salesman problem with help of genetic algorithm. For my bachelor's thesis, I programmed the route between 21 European cities from the database Eurodist available in R. Here are the top solutions I was able to find. Because the genetic algorithm draws the initial population, we can obtain different results each time we run the program. These, of course, were tested and obtained for specific seeds, so they could be repeated with the same result. In the case of finding a route for 21 cities, there are n-1 factorial possible results, which is an astounding number. Thanks to the genetic algorithm, we can obtain an approximate solution in just seconds. Here we can see a graph generated from RStudio. For the shortest path we were able to find for 21 European cities. It doesn't matter which city we are starting our journey from. As you can see, genetic algorithms are very helpful, not only for solving the traveling salesman problem, but they can also be used for optimizing complicated functions as they manage to optimize non-differentiable functions. They can also be used for solving the knapsack problem and many others. If you have any questions regarding this topic, you can email me using the email on screen. Thank you for watching through.